Okay, so picking up where we left off in class today, I want to look at the next example discussing our first derivative. It says use the graph of f prime to identify the intervals on which the graph of f is increasing or decreasing. Now, the number one thing students always get tripped up on the actual AP exam is identifying what is the graph you're looking at. So I'm looking at f prime. So some important things to remember is that when f prime is positive, that means that f is increasing. When f prime is negative, that means f is decreasing. So if we remember this relationship, that allows me to kind of realize I'm going to be looking at where this graph is positive and negative. So I'm going to have an increasing function anywhere that the graph of the derivative is positive. And I'm going to have a decreasing function anywhere the graph of the derivative is negative. So specifically, I'm looking at where is the graph of my derivative positive and negative. So looking at the graph, I'm going to trace over in green anywhere where I have a positive value for f prime of x, and in blue anywhere where I have a negative value. So now using that exact same thing, I can now say that because it starts out being negative, that my actual f, so f is increasing and f is decreasing from negative infinity to -3 because this part of the graph is negative. And then it starts to increase from -3 to 1. Now remember, we're not looking at where f prime is increasing or decreasing. We're looking at the sign of f prime. We're looking at the sign of f prime to tell us what f is doing, okay? So then I'm going to keep going, and I notice I go back negative. So that means that f is decreasing from 1 to 4. And again, we are increasing from 4 to 5. Actually, scratch that. 4 to infinity if this keeps going. Okay? So part B of this says estimate the values on which f has relative maxima and minimum. So relative maximums and minimums. It's important for you to remember that a max happens anytime we have an increasing function go to a decreasing function. So that means I'm looking for f prime to switch from positive to negative. So is there anywhere on my graph where f prime switches from positive to negative? Well, right here, f prime switches from positive to negative. So that tells me that I'm going to have a max at x equals 1. That's the only place where it switches from positive to negative. And similarly, I know that I'm going to have a minimum anytime f decreases and then increases again. So that means I'm looking for anywhere f prime switches from negative to positive. So right here, f is negative, switches to positive. So right here at -3, I have a min at x equals -3. And again, it switches from negative to positive right here at 4. Now, it can be really confusing to look at this graph and kind of try and figure out where its max and mins are because you're thinking about the max and mins of the graph. But the max and mins of f prime are not important here. I want to know where f prime is positive and negative to tell me about f, okay? So I'm going to walk through one more example, and then we're going to switch to the second derivative test. So our next example actually gives us information completely in symbols. It tells us that f prime of x is less than 0 from -infinity to -3. So I think the best way to translate this data into something that makes sense is for us to draw a sign chart. So I'm going to draw a sign chart, and I'm going to label my sign graph as f prime, and I'm going to put -3 on it. And it tells me that it is less than 0, aka negative, from -infinity to -3. And then it keeps on to tell me that the derivative is positive from -3 to +2. So I'm going to go and add +2 to my sign chart. And I'm going to make this a positive derivative. And in the last part, it tells me the derivative is negative again from 2 to infinity. So I'm going to make this negative. Okay, so now that I have my sign chart of f, I'm now going to answer some questions about a new function which we're going to call g. And g has this vertical stretch factor of 2 on it. And the first question says, what is g prime of -1? Well, if I'm going to stretch something by 2, are my signs of the slopes going to change? If I'm going to stretch something by a factor of 2, it's just going to get taller, but my signs of my slopes will not change. So g prime of -1 will be doing whatever -1 is doing, and -1 is located right here. So it's going to be exactly the same as whatever the sign of f prime of -1 is, and it's positive right there. So it will be greater than 0. Okay? For part B, it says, I now am going to say g of x equals f of 3x minus 5. And it wants to know what is g prime of -1. Well, if I take that and I plug in -1 into this expression, I have f of 3 times -1 minus 5 and I should erase this prime symbol right here because technically we're not doing a prime yet. So I just want to know what is g of -1. So if I do that, I find that this is equal to f of -8. So g of -1 is equal to f of -8. So why don't I just figure out what f prime of -8 is, because that will be approximately equal to g prime of -1. Well, where's -8 located? -8 is located right there, and that is negative, so therefore this will be negative. Okay? I'm going to pause right there, and I'm going to switch gears real fast so we can talk about the second derivative. So I did skip an example talking about a particle moving left and right, and if we have time, we might go back to it, but I really wanted to dive into what is probably the most important thing of this video. So today in class, we talked about first derivatives and what they tell us. So we've learned so far that I have f prime and f double prime. And all I know about these functions is that when f prime is positive or negative, that tells me f is increasing or f is decreasing. So we need to figure out, what does f double prime tell us? And f double prime tells us about something called concavity. Concavity. And we describe concavity in 2 ways. We can either say that something is concave up or something is concave down. Now, the way that my teacher in high school described this to me was that if something is concave up, we're talking about concave up like a cup. So she actually drew a little cup of coffee. So concave up like a cup, and that's a pretty terrible drawing of coffee. And concave down, when we talk about concave down, we're saying concave down like a frown, okay? And we can determine the concavity or bend in our graph based on what the second derivative is doing. So the concavity something will be concave up if f prime is increasing on the interval, or in other words, if the derivative has a positive slope. Something will be concave down if f prime is decreasing on the interval. In other words, the derivative has a negative slope. Okay, we're going to come back to this in a second. Now, probably the more easy relationship, the easier relationship to discuss is the test for concavity. The test for concavity. We know that if the second derivative is positive, we say that the function is concave up. We also know that if the second derivative is negative, that the function is concave down. Which now brings us to our fun chart. Our fun chart, which we've only kind of partially filled in. So now I have f prime, f double prime. And really, what's going on here is a couple of different relationships that are super important. And I'm going to run out of room, okay? So first and foremost, I know that if the derivative, the second derivative is positive, my function will be concave up, okay? I also know, based on what we just wrote, that if the second derivative is negative, f will be concave down. So our second derivative tells us about concavity, the bend or shape of the graph. But what's really cool, though, is that it also tells us things about the first derivative graph. For instance, I know that if the second derivative is positive, that the first derivative graph will be increasing, and the second derivative graph will be decreasing, okay? I also know that if my first derivative is positive, my function will be increasing. If my first derivative is negative, my function will be decreasing. So it's almost like it works backwards. Second derivative tells us about concavity. First derivative tells us about increasing or decreasing, but we can almost work backwards one step. So there's this thing called an inflection point. An inflection point is kind of like a critical point. An inflection point happens in two places. It's either where the second derivative equals 0, or the second derivative is undefined. And what a point of inflection does, it's where our second derivative will change sign from either positive to negative, or from negative to positive. It also happens when my first derivative changes from increasing to decreasing, or from decreasing to increasing. And we can see that relationship here. If my first derivative is changing from increasing to decreasing, that also tells me about the concavity of my graph. So what does a point of inflection actually look like? On my graph, a point of inflection is something like this, where I am going to switch the bend or shape of the graph. For instance, if I look at this piece here, I can see that this piece here has a concave down shape. And this piece right here has a concave up shape. But at the point where they change, we call that a point of inflection. Point of inflection. Okay? So how do I use all of this stuff? My first example says, the graph of f is shown below. State the signs of f prime and f double prime on the interval. So recall our fun chart. Fun chart says f prime, f double prime. If f double prime is positive, we know f is concave up. If f is negative, f double prime is negative, f is concave down. But it also tells me that this is increasing and decreasing. I then also know that if f prime is positive, my function is increasing, and if f prime is negative, my function is decreasing. So now using this chart, let's write down what we know. I notice that this graph is decreasing everywhere. This is my graph of f. It's decreasing everywhere. So at every single point on this graph has a negative slope. So that means that f prime is negative because everywhere on the graph has a negative slope. The next thing I noticed is that it has a bowl shape that's kind of concave up like a cup. So therefore, if it's concave up, that tells me that my second derivative must be positive. And now I've established the signs of both my first and second derivative. Skipping on to the next example, I'm given a function, and I now need to be able to tell a bunch of stuff about it. Over to the side, I want you to press pause on the video, and I want you to take a minute, and I want you to write your f prime, f double prime fun chart. So positive, negative, concave up, concave down. That means that f prime is going to be increasing and decreasing. If f prime is positive or negative, then f is increasing or decreasing. So there's my relationships. So whenever I go to do this, the first thing we're going to do in this case is we're going to find our derivatives before I answer any of these questions. So I'm going to find f prime of x is equal to 4x cubed minus 12x squared. And I also know that my second derivative is 12x squared minus 24x. Okay? I'm going to set my first derivative equal to 0. 4x cubed minus 12x squared. And we're going to find our critical points. I'm going to take out a 4x, leaving me 4x squared, leaving me with x minus 3, giving me the following critical points. I have a critical point at x equals 0, and I have a critical point at x equals 3. On the right-hand side, I'm also going to set my second derivative equal to 0, because these are going to give me my possible points of inflection. I'm going to take out a 12x, which leaves me x minus 2. And I'm going to get some critical points here, some possible points of inflection, x equals 0 and x equals 2. Now what we're going to do with these is process them by putting them on a number line, putting them on a sign chart. Being sure to label your sign charts as f prime and f double prime. We're going to put all of our critical points on them. I'm going to put 0 and 3. And 0 and 2 as my possible points of inflection here. Okay, so now what we're going to do is test the signs of our first and second derivatives by plugging in numbers like we did in class today. So if I plug in a number less than 0, this is always going to be positive over here. This will always be positive. So I will have a positive number times a negative number. So that should give me a negative number. If I pick a number between 0 and 3, say 1, I should still end up with a negative number in here. And if I pick a number bigger than 3, then this should be positive. So what does that tell me? That tells me that my function f is going to be decreasing, decreasing, and then increasing. So then I'm going to do the same thing with my second derivative. I'm going to plug in a point over here. So say -1. If I plug in -1, it's going to give me a negative times a negative, which is a positive. If I plug in a number in between 0 and 2, say 1, I'm going to get a positive times a negative, which is negative. And if I pick a number bigger than 2, say 3, I'm going to get a positive number. So what does that tell me about f? That means that f is going to be concave up, concave down, and then concave up again. Okay? So now I'm ready to process this all and come up with my answers. Part A says, find the intervals where f is increasing and decreasing. So I've already established, based on my sign chart right down here, everywhere that f is increasing and decreasing. So now I just have to put that into symbols. F is going to be increasing. It's going to be decreasing to start out with. So from negative infinity to 0. And then it will increase from 0 to 3. And then decrease again. Oh, goodness, I'm already messing up. I'm sorry, guys. I was worried about my stylus not working, and I messed this up. That is completely my fault. All right, try again. It's decreasing from negative infinity to 0. It's still decreasing from 0 to 3, and then it's going to be increasing from 3 to infinity. 3 to infinity. I'm now ready to answer part B. To do this, I'm going to scroll up. The really nice part about writing my F behavior underneath my sign chart here is that I can see that this spot right here is the only place that I'm going to have any kind of extrema. It's going to give me a max of none and a minimum at x equals 3, because this is the only spot where my derivative changes from negative to positive, yielding a minimum. Part C says the intervals in which f is concave up or down, concave up or down. So my function is concave up right here and right here. So I'm now going to say my function is concave up from negative infinity to 0 and from 2 my stylus sucks. I'm sorry. And from 2 to infinity. And we know that my graph is concave down from 0 to 2. And guys, I don't know why my stylus isn't working right. That should say 0 to 2. I'm going to press pause and switch styluses really fast. Okay, the very last part of this graph asks for inflection points, and I know that my work is getting really terribly sloppy here, but we're going to scroll down and remember that an inflection point happens whenever our concavity changes. So right here at 0, my concavity changes. Again, at positive 2, my concavity changes. So I have 2 points of inflection. I have a point of inflection at 0 and a point of inflection at 2. Okay? One of the things you need to be able to do is to put together some curve sketches. Some curve sketches where you guys take given information and piece together a curve. Okay? So I'm going to do one with you, and then I want you guys to try one. So it tells me, first off, in this first one, that f of 0 equals f of 2 equals 0. So I'm actually going to say f of 0 equals 0, and I'm going to draw that point. And f of 2 equals 0, and I'm going to go ahead and put those points on the graph. Now it actually tells me that f prime of 1 is 0, so I know that the slope at 1 is 0. And I see that my derivative is positive for x less than 1. So here's 1. My derivative is positive, which tells me that my function should be increasing. And my derivative is negative for anywhere bigger than 1, which tells me that f is decreasing. So basically, I need something to where it's going to increase and then decrease. I need my graph to increase and then decrease. And at this point, the slope is 0. The next thing I know is that my second derivative is negative, which means it must be concave down. Well, that's a dead giveaway that the only graph that I'm going to be able to construct here is a parabola, because my parabola is going to increase and then it's going to decrease, and it is concave down always. So I'm going to press pause. I want you guys to try and sketch letter B. Try and sketch letter B. Okay, so if you're coming back, here's what I drew. I said, well, it's going to have to increase and decrease again. So I looked for an increase and decrease in my function. Well, what's different about this one is it tells me that the concavity must be facing upward, but I have to have an undefined slope. Well, I said, okay, if I have to have an undefined slope, maybe I have a vertical tangent line drawing right there. So I drew something that had a cusp at 1. And that's kind of the easiest way to throw something like that up. Which brings us to what I'm really wanting us to get to, which is the second derivative test. The second derivative test says we're going to let f be a function, and it's going to have a second derivative. If the derivative is 0, and I want you to underline that derivative, the concavity is positive, so I have an upward-facing concavity, then that actually tells me that the point C, f of C, is a minimum of f. If I know that the first derivative is 0, and the second derivative is negative, then my point is a max. Now what this does is we use this as a justification for maxes and mins, okay? Here's what this says. This says I have a point that has a slope of 0, and I have a concave up function. If I have a concave up function and a place where my slope is 0, it has to be a min mathematically. If I have a concave down function, it has a slope of 0. If I can prove that it's concave down and has a slope of 0, then this point has to be a max. Now what the derivative test does is if the first derivative is 0 and the second derivative is 0, then we actually cannot use the second derivative test, and we would have to go and use the first derivative test. So what the derivative test does is it tells us if something is a max or a min, okay? So let's run through a quick example. I've got a nice pretty polynomial function f of x, and what I want to do is use the second derivative test to see whether there is a local max or a local min at x equals -3. I'm going to take the derivative. 2/3 x to the third is going to be 2x squared. 1/2 times 2 will be just 1, so just 1x minus 15. Now we're still going to take this And you're still going to set this equal to 0 because I need critical points. This factors into 2x minus 5 and x plus 3, giving me critical points of 5/2 and negative 3. Now here's what we're going to do with these. Normally, we would verify using a first derivative sign chart that the function increases and then decreases to make them maxes or mins. But we're going to do something else. I'm actually going to find my second derivative. So continuing from this function, my second derivative would be 4x plus 1. And what I want to do is take these two function values and we're going to plug them in. I want to know what f double prime of 5/2 is. And I want to know what f double prime of negative 3 is. So we're going to plug these points into our second derivative. By plugging them into our second derivative, it tells us if I have a concave up or concave down function. So I'm going to say 4 times 5/2 plus 1. That's going to give me 20/2, which is 10. 10 plus 1 is 11. 11 is a positive number. If I have a positive number, that means that x equals 5/2 is a minimum. Now you might be like, why is that a minimum? If it's a positive number, that tells me that this function is concave up here, and therefore is a minimum. A positive second derivative means concave up. 5/2 has to be a minimum since it's a positive second derivative. And I'm going to do the same thing with negative 3. I'm going to say 4 times negative 3 plus 1. And I get negative 12 plus 1, or negative 11. Negative 11 is a negative number. That tells me my second derivative is negative. So therefore, x equals negative 3 is a max. And we would justify by saying this is from the second derivative test. From the second derivative test. Okay? Let's do another one. I've got a nice, pretty fun trig function. And it tells me f of x equals negative 2 cosine x minus x. So first thing I'm going to do is take the derivative. Take the derivative, I get negative 2 negative sine x minus 1, which I'm going to simplify to be positive 2 sine x minus 1. We are still going to set the derivative equal to 0. Still setting equal to 0, and I'm going to solve. So I know that this is 1/2 equals sine x, and my critical values are where sine equals 1/2. So pi 6. And sure enough, they're asking me to check to see if pi 6 is a local max or a local min. To check to see if this is a local max or min, I need to find my second derivative. So I'm going to take the derivative of this function. Derivative of 2 sine x is 2 cosine x, and the derivative of minus 1 is 0. And what I'm going to do is take this second derivative and plug in pi 6. Because if I know what the sign of the second derivative is, I know the concavity. So 2 cosine of pi 6. The cosine of pi 6 is going to be square root of 3 over 2 times 2. So I get the square root of 3. The square root of 3 is a positive number. Since this is a positive number, that tells me that f is concave up and x equals pi 6 is a minimum value. And we're going to add in by the second derivative test. Okay? I'm going to press pause for a second. So I know I'm running pretty long on this video, but I want to get through 2 more examples and call it a day. 2 examples, okay? So the next one says, use the second derivative test, if possible, to find the relative extrema of this graph. So we're just finding any relative extrema. Step 1, find the first derivative. First derivative is going to be 6x squared plus 6x minus 12. Still setting this equal to 0, I'm going to take out a 6 and factor. I get 2 critical points, -2 and +1. Okay? Now normally, the first derivative test, we would put these on a sign chart, see where f is increasing or decreasing, and be able to verify it this way. But using the second derivative test, like it asks me to, what I need to do is find my second derivative. So 12x plus 6, and I'm going to evaluate these points at the second derivative. F double prime of -2 and f double prime of 1. If I know the sign of the second derivative, I can determine if it's a max or a min. So 12 times -2 plus 6 gives me a function value of -24 plus 6, or -18. That is less than 0. That means that the function is concave down. Concave down means that this point is a max. So x equals -2 is a max. Okay? And then I'm going to go do the same thing here. I'm going to say 12 times 1 plus 6, and I'm going to get +18, which is a positive number. Tells me the second derivative gives f being a concave up function, which means that x equals 1 is a minimum value by the second derivative test. And I actually think I'm going to stop there because these next 2 are some composite functions I want to talk about in front of you. We'll do those at the beginning of class next class. So we'll do 2 composite functions, and we're going to do the curve sketching example on the very last page and be done. Next class is completely a work day, and your quiz, your take-home quiz is due. So guys, I hope you have a great evening. Thanks, appreciate it. See you tomorrow.